Good day everyone! We are going to discuss Chapter 6, the Mathematics of Graphs. Did you know that the Mathematics of Graphs has 5 subtopics? They are Introduction of Graph, Constructing a Graph, Equivalent Graphs, Contrasting Puzzle, and Graph Coloring. In this video lesson, we are going first to discuss the introduction of graphs. Are you ready to learn new things about mathematics? So let's get started. Let me first let you know what a graph means. A graph is a set of points called vertices and line segments or curves called edges that connect vertices. In addition, a graph can be defined as a pictorial representation or a diagram that represent data or values in an organized manner. The points on the graph often represent the relationship between two or more things. Graph can be used to represent many different scenarios. For instance, the two graphs in Figure 6.2 are the same graph as in Figure 6.1, but used in different contexts. In Part A, each vertex represents a baseball team, and an edge connecting two vertices might mean that the two teams played against each other during the current seasons. The graph in Part B could be used to represent the flights available on a particular airline between a selection of cities. Each vertex represents a city, and an edge connecting two cities means that there is a direct flight between two cities. We come now to example number 1, constructing a graph. The following tables list 5 students at a college. An X indicates that the 2 students participate in the same study group this semester. A. Draw a graph that represents this information where each vertex represents a student and an edge connects two vertices if the corresponding students study together. B. Use your graph to answer the following question. Which student is involved in the most study groups with the others? Which student has only one study group in common with the others? How many study groups does Laura have in common with the others? In letter A, we draw 5 vertices to represent the 5 students and connect vertices with edges according to the table. In the letter B, the vertex corresponding to Amber is connected to more edges than the others, so she is involved with one study group in common, as her vertex is the only one connected to just one edge. Laura's vertex is connected to 2 edges, so she shares 2 study groups with others. Check your progress 1. The table below lists 5 mobile phone companies and indicates whether they have agreements to roam onto each other's networks. Draw a graph that represents this information, where each vertex represents a phone company. An edge connects 2 vertices if the corresponding companies have a roaming agreement. Then use the graph to answer the question. Which phone company has roaming agreements with the most carriers? Which company can roam with only one another network? In general, a graph can include vertices that are not joined to any edges, but all edges must begin and end at the vertices. If 2 or more edges connect the same vertices, they are called multiple edges. If an edge and an ends at the same vertex, it is called a loop. A graph is called connected if any vertices can be reached from any other vertex by tracing along edges. A connected graph in which every possible edge is drawn between vertices is called a complete graph. Several examples of graphs are shown below. The first graph has 5 vertices but no edges. It is not connected. The second one is connected graph that has pair of multiple edges. Note that the 2 edges cross in the center, but there is no vertex there, unless a dot is drawn. The edges are considered to pass over each other without touching. The third graph is not connected. It consists of two different sections. It also contains a loop. The last graph is a complete graph with 5 vertices. It does not matter whether the edges are drawn straight or curved, and their lengths are not important, nor is the placement of the vertices important. All that matters is which vertices are connected by edges. Consequently, the 3 graphs shown below are considered equivalent graphs because the edges form the same connection or vertices in each graphs. If you have difficulty seeing that these graphs are equivalent, use the labeled vertices to compare each graph. Note that in each case vertex B has an edge connecting it to each of the other 4 vertices, and no other edges exist.
Example number 2. Equivalent graphs determine whether the following 2 graphs are equivalent. Solution. Despite the fact that the 2 graphs have different arrangement of vertices and edges, they are equivalent. To illustrate, we examine the edges of each graph. The first graph contains 6 edges. We can list them by indicating which 2 vertices they connect. The edges are AC, AE, BD, BE, CE, and DE. If we do the same for the second graph, we get the same 6 edges because the 2 graphs represent the same connection among the vertices. They are equivalent. Check your progress number 2. Determine whether the following 2 graphs are equivalent. To illustrate, we can say that the 2 graphs are the same based on their vertices and edges. They are equivalent. We examine the edges of each graph. The edges are AC, AE, CB, EB, AD, DB. If we do another graph, it is the same as the first graph with the same 6 edges. Picture. The internet is a graph. Graph theory is playing an ever-increasing role in the study of large and complex systems, such as the collection of web pages that are published on the internet. The image below, created by Mae Q is an illustration of various blogs that appears on the web. Each vertex represents a particular blog and 2 vertices are joined by an edge if one of the corresponding blogs contains a link to the other. You can imagine how large the graph would be if all the millions of existing blogs were included. Another example of an extremely large graph is the graph that uses vertices to represent telephone numbers. An edge connected 2 vertices if a phone call was placed from one number to the other. James Avilo of AT&T Shannon Laboratories analyzed a graph formed from one-day word call. The graph had over 53 million vertices and 170 million edges. Interestingly, although the graph was not a connected graph, it contained 3.7 million separate components. Over 80% of the vertices were part of one large connected component. Within this component, any telephone number could be linked to any other through a chain of 20 or fewer calls. Euler circuits. To solve the Königsberg bridges problem presented, we can represent the arrangement of land areas and bridges with the graph. Let each land area be represented by a vertex and connect 2 vertices if there is a bridge spanning the corresponding land areas. Then the geographical configuration shown in figure 6.3 becomes the graph shown in figure 6.4. In terms of a graph, the original problem can be stated as follows. Can we start at any vertex, move through each edge once but not more than once, and return to the starting vertex? Every attempt seems to end in failure. Before we can examine how Euler proved this task impossible, we need to establish some terminology. A path in a graph can be thought of as a movement from one vertex to another by traversing edges. We can refer to our movement by vertex letters. For example, in the graph in figure 6.4, one path will be AB, AC. If the path ends at the same vertex at which it started, it is considered a closed path or circuit. For figure 6.5, the path ABFGE is a circuit because it begins and ends at the same vertex. The path ADFGEH is not a circuit, as the path ends at a different vertex than the one it started at. A circuit that uses every edge but never uses the same edge twice is called an Euler circuit. The path may cross through vertices more than once. The path BDFGHECBADGEB in figure 6.5 is an Euler circuit. It is begin and ends at the same vertex and uses each edge exactly once. The path ABCEHGEBDA is not an Euler circuit. The path begins and ends at the same vertex, but it does not use edges DF, DG, or FG. The path ABCEHGFDABEGDA begins and ends at A but uses edge AB twice, so it is not an Euler circuit. All of this related to the Königsberg-Bridges problem in the following way. Finding a path crosses each bridge exactly once and return to the starting points is equivalent to finding an Euler circuit for the graph figure 6.4. Euler essentially proved that the graph in figure 6.4 could not have an Euler circuit. He accomplished this by examining the number of edges that meet at each vertex. The number of edges that meet at a vertex is called the degree of a vertex. Consequently, such graphs are called Eulerian. He made the observation that in order to complete the desired path every time you approach a vertex, you would then need to leave that vertex. If you travel through that vertex again, you would again need an approaching edge and a departing edges. Thus, for an Euler circuit to exist, the degree of every vertex would have to be an even number. Furthermore, he was able to show that any graph that has even degree at every vertex must have an Euler circuit. Eulerian graph theorem. A connected graph is Eulerian only if every vertex of the graph is of even degree. Example number 3. Identify Eulerian graph. Which of the following graph has an Euler circuit? Solution. Vertices C and D are of odd degree by the Eulerian graph theorem. The graph does not have an Euler circuit. All vertices are of even degree by the Eulerian graph theorem. The graph has an Euler circuit. Check your progress tree. Does the graph shown below have an Euler circuit? A graph is a collection of vertices or nodes and edges between some or all of the vertices. When there exists a path that traverses each edge exactly once, such that the path begins and ends at the same vertex, the path is known as an Eulerian circuit, and the graph is known as an Eulerian graph. Eulerian refers to the Swiss mathematician Leonhard Euler, who invented graph theory in 18th century. That graph showed that each edge visits each edges in the same way they contribute points, and allowing each part to connect edges to build Euler path or Euler circuit. In figure 6.4, the graph representation of the Königsberg bridges, because not every vertex is of even degree. We know by the Eulerian graph theorem that no Euler circuit exists. Consequently, it is not possible to begin and end at the same location near the river and cross each bridge exactly once. There is a systematic method called Fleury's algorithm that can be used to find the Euler circuits in graph with larger number of vertices. Example number 4. Find an Euler circuit. Determine whether the graph shown below is Eulerian. If it is, find an Euler circuit. If it is not, explain how you know. We shall verify that the given path in the Euler circuit start at vertex B and trace along the edges of the graph following the vertices in order. Make sure you trace over each edge once but not twice. Solution. Each vertex is of even degree 2, 4, or 6. So by the Eulerian graph theorem, the graph is Eulerian. There are many possible Euler circuits in this graph. We do not have a formal method of location one, but by trial and error, one Euler circuit is B, A, F, B, E, F, G, E, D, G, B, D, C, B.
Check your progress for: does the graph at the left have a Euler circuit? If so, find one. If not, explain why. As we observe at the graph, we must say that it is a yes, because it shows the real circuit that shows how this edge visits each edge. Example number 5, application of Euler circuit. The subway map below shows a track that subway trains traverse as well as a junction where one can switch trains. Suppose an instructor needs to travel the full length of each track. Is it possible to plan a journey that traverses the track and returns to the starting point without traveling through any position of the track more than once? We can consider the subway map of graph, where the vertex of each junction and edge represent the track that runs between two junctions in order to find the travel route does not traverse the same track twice. So we need to find a Euler circuit in the graph. Note that however that the vertex representing the civic center junction that has a 3 degree. Because a vertex has an odd degree, the graph cannot Euler circuit. It's not impossible for the inspector not to travel at least one track twice. Graph number 5. Given the problem at the graph, would the citizen be able to complete a stroll across each bridge and return to their starting points without crossing the same bridge twice? Let's find out. The bridge represents as the vertices and edges. The island as the basis to show each edges. The citizen able to stroll across each bridge return to their starting points without crossing the same bridge twice. A Euler path theorem is a connected graph contains a Euler path if and only if the graph has two vertices of odd degree with all other vertices of even degree. Furthermore, every Euler must start at one of the vertices of odd degree and end at the other. Example 6. An application of a Euler path. Given the problem, is it possible for the photographer to design a trip that traverses all of the road exactly one? Let's find out. As we know that a Euler path exists, and so it's possible for the photographer to plan a route that travels each roads once because A and D are vertices of odd degree. The photographer must start at one of this city with a little experimentation. We find that one Euler path is A, B, C, D, B, F, A, G, F, E, D. Check your progress 6. Given the problem, is it possible for the cyclist to traverse all of the trails without repeating any portion of the trip? Let's find out. Yes, is it possible for the cyclist to traverse all of the trails with a Euler circuit sample? In that way, the edges can propagate edges to edges. Instead, it will visit the edge point that traces the portion of the trip. Example 7. An application of the Euler path. The following figure depicts a floor plan of an art gallery. Draw a graph that represents the floor plan where vertices corresponds to the room and edges corresponds to the doorways. Is it possible to take a stroll that passes through every doorway without going through the same door twice? If so, does it matter whether we return to the starting points? Let's find out. We can represent the floor plan by a graph. If we let a vertex represent each room, draw an edge between two vertices if there is a doorway between the two rooms as shown in a figure 6.6. While the graph in figure 6.7 is equivalent to our floor plan, if we would like to tour the gallery and passes through every doorway once and no more. Furthermore, we know we must start at a vertex of an odd degree, either room C or B. By trial and error, one such path is C, B, F, B, A, F, E, D, C, F, E. Check your progress 7. The floor plan of the warehouse is illustrated below. Use a graph to represent the floor plan and answer the following questions. Is it possible to walk through the warehouse so that you pass through every doorway once but not twice? Does it matter whether you return the starting points? It is possible, but there are one or two doorways that you can pass through that warehouse has an equivalent representation that may say you can pass on.